Hi guys, in this video we will continue our look at the reactions that are possible with alpha-beta unsaturated carbonyl compounds. And that typically means when we have an alkene that is conjugated with a carbonyl group, such as this molecule here. Now, it doesn't have to be conjugated with a carbonyl group. It could be conjugated with some other electron withdrawing group with a heteroatom, such as a cyano group or a nitro group or a sulfone, which is an SO2 group. A lot like the groups that were required when we did a NAS substitution reaction, and the same type of concept. We cannot add a nucleophile to a regular alkene, a non-conjugated alkene. The resulting anion is not stabilized enough and the reaction won't take place. We also saw that when we were trying to add a nucleophile to the benzene ring, potentially trying to do a NAS mechanism. When we were doing that chemistry, we said the NAS can only occur when the resulting anion can be delocalized to a heteroatom. Okay? And there were some other details here. Ultimately, we can only add a nucleophile to this alkene when the resulting anion can be delocalized, in this particular case, to the oxygen. And because that can happen here, we can indeed do this reaction. So nucleophiles can add to the beta carbon. Okay, we introduced this last time. Let's get to some specifics. Different nucleophiles. Okay. Now let's look at Carbanion nucleophiles, such as Grignards, organolithiums, which always typically react the same. All right. Now these react to give 1,2 products with these alpha-beta unsaturated carbonyl compounds. Where cuprates, if you remember organocuprates, these actually always react to give the 1,4 product. All right. We may try to explain why. It might be a little difficult. But with that statement, let's look at this reaction here. We have this Grignard, methyl magnesium bromide, or methyl lithium, they both react the same, followed by H plus workup. Well, we know the Grignard can be considered as the methyl anion. Of course, that's a CH3 anion. And this gives a 1,2 product, and that involves adding directly to carbonyl, a direct addition. And that's going to give electrons up. We have 1 methyl, but now we have 2, right? I'm not going to clarify that as an Me, but for these are methyls. Game over, end of, okay? It's a 1,2 addition. Just like we said, here's our 1,2 product. We need to protonate it, throw in some water or acid here, okay? And the product will be this alcohol. And that's just a simple direct addition to the carbonyl. All right. Now, once we add the nucleophile to the carbonyl, it's not reversible. Okay? It's not going to reverse because the nucleophile is not, in turn, a good leaving group. Even when we can say, hey, we can use a lone pair, make a pi bond, kick off a leaving group. Well, we never kick off a plain hydrogen or a plain carbon. Okay, we've talked about that before. Okay. The 1,2 product is always formed first. Okay. The 1,2 addition is only reversible if the nucleophile can act as a leaving group. All right. Well, it cannot in this case. That's it. All right. Let's try the same substrate, but now let's react with these organocuprate. You should remember those. We reacted those with acid chlorides. That was a great way to make ketones. All right. It's again the methyl anion, but it just has diminished reactivity. Now, cuprates do add 1,4. And so these electrons will add to the beta carbon. This is where it's a little bit hard to explain this, rationalize this outcome. Let's first show the product. We're going to have a methyl here, just added to that carbon, and we generate an enolate anion. Of course, it's resonance stabilized. And with H plus workup, we will get that product there. This carbon now has 2 H's. Only had 1 here. This lone pair reacts with the H plus. All right. I'm not sure I can explain the magic of copper here, okay? Because you might think, well, wouldn't it be faster to add to carbonyl? Yes, we said that. The methyl adds to carbonyl. How's it going to reverse? It could not. That implies, and indeed it is the case, with copper, it's actually faster for the methyl to add conjugate or to the beta carbon. That's the magic of copper, and that's what I can't really explain. Or I'm not going to try to because it would take a little bit too much time and effort. Probably that copper coordinates somehow with the carbonyl, and somehow it makes the kinetic product be actually the conjugate addition. All right, let's just call it magic. All right, for homework, you can just show the different products from here. This enone, this alpha beta unsaturated ketone reacting either with a Grignard or a organocuprate. That's number 3 and number 2. What was number 1? Okay, well number 1 was just a general overview. Then number 2 we started to getting specific. Number 3, what is number 3? 3 is with heteroatom nucleophiles, such as amines. Now these typically give 1,4 addition products. Now we can rationalize this by saying, yes, the 1,2 addition is the kinetic product, as we stated on the previous page. And yes, this likely adds to the carbonyl first. But if the nitrogen adds, it can then be kicked back off. Okay? Thus, the 1,2 addition is reversible. And if the 1,2 addition is reversible, ultimately we will get an equilibrium established between 1,2 addition and 1,4 addition. And the 1,4 addition will thus become the favored product because under thermodynamic control, the more stable product is your favored product. Ultimately, heteroatom nucleophiles typically give 1,4 addition products. Knowing that, we can just show that mechanism and I didn't leave a lot of room here. Let's show this over here. That's just a cyclohexane. That's going to give anion here, nitrogen here. The nitrogen has a methyl, H, and an H. It's now positive after it did a nucleophilic addition. Well, this molecule, we do not need a proton, a acid workup or water workup. An acidic proton is built in because once the nitrogen becomes positive, this nitrogen is going to want to lose one of these H's and act as an acid. Proton transfer from the nitrogen to the carbon will just give the final product. No external proton is needed in this case. All right, down here we have a heteroatom nucleophile. The O-ethyl anion acts as a nucleophile, adds to the beta carbon, electrons here. That will give now I could show that as an O-ethyl. How about if I show it with the actual line bond? There's your O-ethyl. Okay. Now there's no proton built in here. The oxygen goes from negative to neutral. So where can we get a proton? In this case, we can use a protic solvent and it can supply the proton. And we would get that product, and we would actually reform the O-ethyl anion. So actually the O-ethyl is a catalyst here, and we're adding ethanol here. If you look at the formula, the difference in formula is this molecule now has the O-ethyl and an extra H added to it. The O-ethyl is actually catalyst. It's acting as a catalyst by being a stronger nucleophile, regenerated at the end, but a molecule of ethanol is consumed with each reaction, so it's stoichiometric. What about synthesis? Ultimately, when we do now these were Michael addition. Okay, 1,4 addition is Michael addition. All right. Review. What type of nucleophiles do Michael addition? Heteroatom nucleophiles. Okay. This is Michael. And organocuprates. Those add 1,4, called Michael addition. Grignards and alkyl lithiums do direct addition, not Michael addition. Now, when we do a Michael addition, we are getting a nucleophile added to the beta carbon. So, in terms of synthesis, how would you make a compound? If you see a compound in which you have a nucleophile on the beta carbon, most often the beta carbon refers to beta to a carbonyl, we can envision this coming from alpha beta unsaturated carbonyl compound and reacting that with the nucleophile. Now this would be an amine, and we would use the neutral NH. All right. So this amine would add. Very analogous to here, except we got 2 methyls in this case. When the nitrogen becomes positive, we can do a proton transfer of that H to the enolate carbanion, and that would give this product. Now in this case, we can go back to the same, all right, enone, and we would react this with methyl magnesium bromide, or let's just use iodide in this case, it doesn't matter, just to change it up, with H plus or H2O workup. And that would give that product. Because anytime you have an alcohol, that could come from a direct addition to a carbonyl. And so we back this up to this. I'll just redraw it, give us more room here. There's that. Really, we're not even focusing on that, but we can say we're going to back this up to a carbonyl and envision a methyl adding to a carbonyl electrons to oxygen. And then we can show the reaction. I just did that this way. Okay. All right. Applications. Now before we talk about this, let me just state again that these alpha beta unsaturated carbonyl compounds tend to be pretty electrophilic, particularly the Michael reaction. The Michael reaction tends to be pretty easy with these type of molecules. Okay? I'm not going to fully discuss why. All right? They just tend to be. All right, I said that right here. They tend to be very reactive. All right. Nucleophiles love to add, and heteroatom nucleophiles love to add, do a conjugate addition, do a Michael addition. Very easy. Okay. Now, biological application. There are a good number of anti-cancer drugs that contain an alpha beta unsaturated carbonyl component. Now this is not a ketone, it's actually an amide, but the alkene is conjugated with the amide carbonyl. And nucleophiles in your body will add, okay, to the beta carbon. Now your body has lots of different nucleophiles. And many amino acids have nucleophilic functional groups or atoms. Okay? And it's actually known that with this drug, the amino acid tyrosine, and I believe tyrosine has an OH group. All right? The OH, now in certain cases in the body, it can be an O minus. But that oxygen adds and does a Michael addition. All right. And in this case, that tyrosine is part of an enzyme. Okay. But once the tyrosine residue reacts with this drug, it becomes covalently modified. And then that ultimately inhibits or it inhibits the activity of the enzyme. We could say it destroys the enzyme, but it makes it inactive. Now, if that enzyme is important for the progression of cancer, it can become a drug target, and we can knock out or inhibit that enzyme, and that's the mode of action or how this drug acts at the molecular level. All right. Another application, superglue. If you look at the chemistry of superglue, and I believe it's in the other handout, I'll try to grab that. It's actually a polymerization reaction. Now, superglue can be used to glue things together, like two plastic pieces or something. It's also used, a little bit surprisingly, in medical applications to hold a wound or like a cut, to seal it up and hold the skin together. And for wound closure, and this compound known as Dermabond is used in this small child here with a gash on her forehead has been closed up by using, which is essentially superglue. So some biological or medical application. All right. Toxicity of Tylenol is based on a Michael addition. We can show these a little bit later, maybe in this video or maybe in class. They are in the other handout. So some very important applications to look at related to the Michael addition. Okay, let's look at this mechanism. It involves a Michael addition followed by an elimination. Now, if we look at the reaction, it's an overall substitution. The Cl is replaced by the O-methyl. All right? Supply a mechanism for homework. But again, I tell you right here what's happening. All right? Now, in looking at this mechanism here, we can compare it to the simple NaS, where if we had a chlorine here, we could replace it, substitute it with an O-methyl. Of course, in this case, we know that this is possible because the leaving group has a strong electron withdrawing group, ortho or para. All right, last page of the last handout. Number 6. How would an enolate nucleophile add to an alpha-beta unsaturated carbonyl compound? Well, that's what we're doing here. We've got a base. We've got one of these compounds that has a particularly acidic methylene group, and we would make anion here. Now, if we have this enone, and knowing that enolate nucleophiles add 1,4, that is Michael addition, this would add here, electrons here. This carbon would be bonded to that carbon. We just made this bond, and that carbon would go to this carbon, and that becomes an anion. And this carbon, I've just sort of flipped this molecule over and drawing the carbonyl down, would be that. 4 carbon, 1, 2, 3, 4. Nucleophile added to the beta carbon, electrons to the alpha carbon. But there's our stabilized enolate. We can show resonance structure if we need to or are asked to do. But we can also just take a proton from solvent and we would get our final product. You can draw this however you'd like. How about if I draw it like this? Now the alpha carbon has picked up an H and gone neutral. There's 2 H's here now. There's your product. So enolate anions, including these activated enolates, do Michael additions to enones. Really, the only type of reactants that do direct addition, if you go back and look, are your Grignards and alkyl lithiums. Now, by the way, I like to point out a miscellaneous tidbit here. Some books, particularly advanced books, maybe in graduate level books, will actually show with this reaction that you also get some 1,4 addition product. Now, when you see that, you'll say, well, I learned, Dr. Stevens said that Grignards only do 1,2. Why did he not say you get both? Well, it has actually been proven that if your Grignard is super pure, okay, how would you make this Grignard? You would take methyl bromide or methyl iodide and react it with magnesium metal. And the magnesium would do an oxidative addition and we would get methyl magnesium bromide. Okay, make your Grignard. And if you use super pure magnesium, the resulting Grignard will only add 1,2. All right. But it's been shown if you use less than pure magnesium, okay, just like standard off-the-shelf 98, 99% magnesium, much cheaper, much more common, that actually gives some of the conjugated addition product. So why would pure magnesium give only this, but impure give both? Apparently an impurity is causing this to be formed. Well, guess what a common impurity in magnesium is? Copper. All right? Makes a lot of sense. If you've got a little bit of trace amount of copper in your magnesium, you may get some of this product, okay? Very interesting, yeah? So the next time you look at a reactant, you know, 2-aminofluorine here, it says, well, it says greater than, but it's telling you it's 98% pure. All right? And we often use this, and it works fine. Now, you can maybe try to buy 99 or 100%, but it may not be available, or it may be super expensive. Is it really needed? The question is, what is the other 2% in this solid? Yeah? Okay. Now, I'm showing you this product, but it could actually react further. Okay? Because we get this, we still have ethoxide. It's actually the catalyst here. And the ethanol was just solvent. It didn't react at all. Actually, this molecule could react further with a base catalyst. It could actually do an intramolecular aldol. All right. Now, it could actually give, from there, two different Aldol, now I'm going to clarify that, condensation products by an intramolecular aldol. I will remind you, involves reacting of an enolate, all right, with a carbonyl. Intramolecular, we're going to make a ring. For example, we could get enolate formed here. Ethoxide could take an H, and then this could attack this carbonyl, all right? Or we could have an enolate here. So actually, I'm going to modify this. It could actually be 3. I see now 3 possible products. And the enolate here could attack this carbonyl or this carbonyl. And that would be a 1, 2, 3, 4, 5, 6, or a 6. If this attacked here, it'd be 1, 2, 3, 4, 5. 3 different 6-membered rings. The only other place to make enolate would be here. Now that's the actually most acidic H. And by the way, I'm seeing this is probably not catalyst. Probably not. It's actually not catalyst now. Please see if you can understand why. It's not going to exist like this. This is going to take an H from somewhere and end up as ethanol. So it will not exist at the end. All right. All right. This can do, if we include enough ethoxide, we could get the original Michael product, but then it could undergo an intramolecular aldol reaction. And if you read down here, that 2-step sequence is called a Robinson annulation. And this product, okay, how about if I show 1? All right, I'm going to use the same structure. That's just the Michael product. But what if we then formed anion here and this attacked here? That would give a 6-membered ring. I'll show carbonyl here, and that's this carbonyl. The carbon over here has another carbonyl or ketone bonded to it. That enolate carbon attacks something and may bond to this carbon. This carbon is going to have an O-. Carbon added to carbonyl, electrons on to oxygen, but the carbonyl carbon has 1, 2, 3, 3 carbons between 1, 2, 3 between the 2 carbonyls, but that carbonyl carbon also has this methyl group. And that gives this, all right? And at that point, I'm not going to do full mechanism, but this can pick up an H, all right, aldol mechanism. Let's do proton transfer. Let's just, okay, that's easier enough. H plus transfer. to get us back an enolate anion again. Now we can make that pi bond and kick off that leaving group and show a final product. And this would be our Robinson annulation product. Now, annulation is a fancy term for ring forming reaction. Now, a lot of times you will see just this line reaction given this as the product. Now the first step is a Michael addition of the enolate to the beta carbon, and I showed the original neutral product. But from there we can have an intramolecular aldol, and I showed one possible product from that type of reaction here. Two-step process. A lot of times it can be done in just one reaction flask, one reaction. And when these react to give this product, it's called a Robinson annulation. Now that's a reaction, yeah? Now, as I said, there's more than one possible aldol condensation product. I showed this enolate attacking this carbonyl. What if this enolate attacked one of these carbonyls? All right, there's two other six-membered rings possible. All right, please show those for homework. I would recommend another piece of paper. Now the question could become, well, which of the three is going to be favored? That may be difficult to actually tell. A lot of times that involves doing the reaction and discovering which would be favored, and then going back and trying to explain that. But if you did see this product and said, hey, for example, mechanism, how would you form this by reacting these starting materials? Well, it's a Michael addition followed by an intramolecular aldol reaction. In graduate school, my second organic chemistry class, the final exam was one question. And it was this here: starting with commercially available reagents, propose a synthesis of the following compound known as isoiresin. Your synthesis should be stereoselective. Well, there's a variety of possible routes, and it looks fairly complicated. But one strategy is to do a Robinson annulation, and you can back it up to these two starting materials. All right. Now these may have to have been made from commercial reagents, but these two will react, okay, in the presence of base, to give this product. We had one ring, but now we have two. And from here you can work your way towards isoiresin. But if you look at this, this reaction gets you the two rings here, okay, and it gets you some other functional groups. Now you need to build one more ring up here. All right. Now this product, it's a natural product. It was actually first synthesized at UGA in Athens in the late 1960s, published in the Journal of the American Chemical Society. But the first step in the mechanism is forming anion here, and then these electrons doing a Michael addition to this enone. On another piece of paper, see if you can work your way, okay, to this product. It's analogous to what we did above. A Michael addition followed by an intramolecular aldol. It's actually pretty straightforward. All right. So there's a nice example of a Robinson annulation. Okay, guys. Well, there's your final exam. I think I have my final exam from graduate school. I was just looking at it. Let me see. Yes, it's my actual exam. And my grade, super approach, yes. Several years ago. Okay, guys, that is actually our last handout. Looking at the chemistry alpha to carbonyls.